We are going to continue to talk about the reactivities of the carboxylic acid derivatives. At this time, we are going to be focusing on the preparation of acid anhydrides. Anhydrides can be synthesized by excessive heating of a carboxylic acid. Here we have the example of taking acetic acid, heating it to 800 degrees Celsius, and producing acetic anhydride, and water is going to be the byproduct. Now, understand that this excessive heating reaction only works for acetic acid to make acetic anhydride. Most carboxylic acids, if they are undergoing this reaction, they cannot survive the extreme temperature. So we have to find a way to efficiently make our acid anhydrides that does not include this excessive heating. The most practical way to synthesize acid anhydrides is by reacting an acid chloride with a carboxylate anion. And as you can see, that is illustrated on the reaction, the general reaction that we have on or after the first bullet point in the slide. When it comes to the mechanism for this reaction, as you can see, this is essentially under basic conditions. In the first step of the reaction, the oxygen that is negatively charged in our carboxylate anion is going to attack the carbon in the C double bond O of our acid chloride, and the electrons go up to the oxygen. After we form that alkoxide tetrahedral intermediate, we are going to have the reformation of the C double bond O in our intermediate, and when the electrons come down from the oxygen, that is going to actually kick out the leaving group that in this case is going to be the chloride anion. And as you can see, that is going to result in the formation of an acid anhydride. Given the fact that there is quality leaving groups, okay, and the reactivity of the anhydrides is actually pretty similar of the acid chlorides. So in the acid chlorides we saw in the previous part of this chapter, chloride is a good leaving group. So in this case, as you can see, our leaving group is going to be that oxygen atom that is single bonded to the C double bond O and that is attached to the R group. Okay, understand that it is not necessary to use pyridine with anhydrides because a strong acid is not generated as a byproduct in these reactions. So instead of going over every single one of the reactions, as we just illustrated for the acid chloride in this slide, and specifically in your textbook, if you have the third edition of the textbook, figure 20.10 shows you how anhydrides can undergo many reactions that are very similar to acid chlorides. And I'm just going to number them similar to what I did previously in this chapter. So the first reaction that we observed here is that if you take an acid anhydride and you react it with an alcohol, you will be forming an ester. Reactions 2, 3, and 4 are reactions for the formation of an amide. As you can see, in reaction 2, we have excess ammonia to make an amide that has 2 hydrogens on the nitrogen. And as we have substituted amines on reaction 3 and 4, then we are going to create substituted amides specifically at the nitrogen. On reaction number 5, we have the reduction of an acid anhydride. And understand that when that happens, we are also going to be forming that primary alcohol. On reaction number 6, as you can see, we can selectively have that reduction stop at the aldehyde by utilizing that modified aluminum reagent, that is the tributoxy aluminum hydride. On reaction 7, as you can see, if we take a Grignard reagent with an acid anhydride followed by a acidic workup, we're going to form that tertiary alcohol. On reaction number 8, we can selectively stop at the ketone by using the Gilman reagent. And remember that whatever alkyl group is in that R group next to the CuLi is what gets incorporated, or it substitutes, in this case, the portion of the molecule that I'm going to highlight in lavender. Remember, this portion of the molecule is what gets substituted, specifically when we do reaction 8 using the Gilman reagent. As you can see, acid anhydrides can also undergo hydrolysis to produce a carboxylic acid when you react them with water. And to actually produce the acid anhydrides, if you start with it, is by number 1. Let me number this. So this is number 9 is the hydrolysis. Number 10 is the production of an acid anhydride. So in number 10, as you can see, the first step of the reaction, when we are adding a base, that's going to create a carboxylate. And then that carboxylate can be reacted with an acid chloride. So step number 2, that is going to be the acid chloride. And understand that when you take a carboxylic acid and you heat it to make an anhydride, this reaction number 11, I'm going to highlight it in red. And the reason is that reaction number 11 only works for acetic acid forming acetic anhydride. So it doesn't work for every carboxylic acid. Let's now talk about the preparation of esters. Esters can be prepared by SN2 reaction of a carboxylate with an alkyl halide. As you can see in the first step of the reaction, we are just going to add base to our carboxylic acid to produce a carboxylate. Once you have the carboxylate, that O negative in the carboxylate, I'm just going to draw out. So in step 1, the product of that reaction is the following. And in the second step of the reaction, you can envision that that oxygen that is negatively charged is going to add to the carbon atom, and then that's going to kick off the iodine. Now, understand that NaOH is used to deprotonate the carboxylic acid. And again, that's how we produce the carboxylate that I drew on item number 1. One of the very common ways to be making esters is by Fischer esterification. That is a very popular reaction. In Fischer esterification, what we're doing is that we're combining a carboxylic acid and an alcohol in the presence of acid in order to make the target ester. Understanding in this process, we are going to be forming water. Our acid is just an acid catalyst, Okay, so that is just going to help us to increase the rate of the reaction and to get to product. The mechanism for this instant is consistent with the one that occurs under acidic conditions. So we are going to see in the next slide how that process actually occurs. Because of Fischer esterification occurring under acidic conditions, then the first step of the reaction is going to be the protonation of the oxygen in our carboxylic acid. So we have to make that carboxylic acid being a better electrophile. Once we have that protonated carboxylic acid, then our alcohol, and remember that alcohols are not going to be the strongest nucleophile. So that's why catalytic acid is needed, because we need to make that carboxylic acid a better electrophile so our not so strong nucleophile can go and add to the carbon in the carbonyl, which is exactly what we see in the second step of that nucleophilic attack. The oxygen atom in the alcohol is going to attack the carbon in the carbonyl, putting the electrons up to the oxygen. Once that happens, as you can see, we're going to be forming that specifically tetrahedral intermediate that then it undergoes deprotonation. So as you can see, by the time that we get to this molecule that I marked with a check mark, what happens is that we have another proton transfer, because overall, since the OH that we started with, I'm just highlighting it in blue, we need to make it leave the system, and we're under acidic conditions. We cannot designate that this is going to just be a good leaving group. A strong base is not a good leaving group, especially if we are under acidic conditions. So that second proton transfer is such that when that OH leaves, it's going to leave in the form of water. So as you can see, we're going to protonate that OH. That OH now can leave in the form of water, and under acidic conditions, that is the best way that we can propose that it's the way that is going to form. So the electrons from the OH, you can see specifically the oxygen atom is going to take one of its lone pair, push down to reform that C double bond O, and in turn we're going to have a loss of water. And in the last step of the reaction, we're going to have a proton transfer in which we're going to remove that proton from the carbon oxygen double bond to form the ester. Understand that the mechanism of Fischer esterification has been studied heavily. And one of the ways that has been proven in the way that it proceeds is specifically through looking at isotope labeling. This is not something that you guys need to study in detail, but just understand that this is one of the ways in which it was shown how the oxygen atom in the alcohol actually gets incorporated into the ester. Now, Fischer esterification is an equilibrating process. Water must be removed in order to favor the formation of that ester. So understand that in order for the reaction to be pushed into forming the ester, we need to be removing the water. So this is in a way bringing the concepts of Le Chatelier's principle, that since you are removing one of the products, is going to move or push the rate of the reaction in the forward direction for specifically here the formation of the ester. So understand that removal of water is kind of putting the Le Chatelier's principle in the forefront for making the ester under Fischer esterification conditions. Esters can also be prepared by treating acid chlorides with an alcohol, as we saw previously. And understand that in this process, we require the formation of pyridine, or not the formation, sorry, the addition of pyridine, just because there's HCl form in the reaction. So this reaction specifically, we saw previously in this chapter. When it comes to the reactions of esters, understand esters can undergo hydrolysis. And hydrolysis, in this case, means that we are lysing, meaning cutting. Hydro means water. So the hydrolysis that we saw before was just more like the addition of water to form a functional group. We actually can see here how water is going to split our molecule into two. So when esters undergo hydrolysis under basic conditions, what we are doing is on step 1, we're adding base. On step 2, we're doing an acidic workup. And overall, understand that when we have hydrolysis of an ester, we are going to form a carboxylic acid and an alcohol. So, how do you know which part of the molecule is which? As you can see in the labels that we have, the group that is bonded to the single bond oxygen in the ester is what is going to be part of the alcohol. Whatever group is attached to the C double bond O, that's what forms the carboxylic acid. So when hydrolysis is occurring in an ester, in essence, I'm just going to do a green dotted line. What we're cutting the molecule is here, where the left side of the molecule, meaning the C double bond O, and whatever is attached to it is what converts into the carboxylic acid. The right side of the molecule, but in this instance, is just how the ester is drawn. So understand that it's always by the way that things are bonded. So that single bond oxygen with whatever is attached to it is what converts into an alcohol. So do not always assume that it's going to be the right side is the alcohol, the left side is going to be the carboxylic acid. It always depends on how your ester is drawn. So go by the attachment of the atoms. Let me just repeat that one more time. When you have an ester, the part of the molecule that is single bond oxygen with whatever R group, that's what turns into the alcohol. The part of the molecules that is C double bond O with the R group, that turns into carboxylic acid. In this instance, this ester is drawn as, you can see, as a C double bond O with its R group, single bond to oxygen, and then the R group that we see on red. So that's why we have the result. But if it was flipped, then remember, it's about the attachment of the atoms. When it comes to this, as you can see, an acidic workup is necessary to obtain a neutral carboxylic acid, because under basic conditions you can envision that what we make in that first series of steps is a carboxylate. So let's go over the mechanism so we can observe why is that the acidic workup is necessary. So in the first step of the reaction, we're going to have the hydroxide ion function as a nucleophile that is going to attack the carbon in the carbonyl in our ester, and the electrons are going to go up to the oxygen. We're going to make a alkoxide intermediate. Once that alkoxide intermediate is formed, remember, we're under basic conditions. So this means that we can actually have the electrons from that oxygen that is negative come down and have an alkoxide leaving group being formed. Remember that alkoxide ion that gets expelled from the molecule can occur because the first step of the reaction of base hydrolysis, we're under basic conditions. So it is okay to propose that that molecule is going to form. Now, since you form an alkoxide, we already learned previously that alkoxides are strong bases. So since in that step 2, when we have the reformation of the carbonyl and the leaving or the expelling of the OR group is happening, we form a carboxylic acid that can be easily deprotonated by the alkoxide. So overall, in the first step of these series of reactions, again, when we are under basic conditions, we are going to form that carboxylate ion, which is illustrated here. And in the process, as you can see, we already make the alcohol in the system. Now, understand that once this is formed, the reason why we have the step 2 with the acid is so you form the carboxylic acid, because we need to protonate it, since in these steps we form under the basic conditions in the beginning, we're going to form a carboxylate ion. Now, understand that hydrolysis, specifically of esters, can also happen under acidic conditions. So this is going to be the acid hydrolysis of esters. Okay, and when that occurs, as you can see, the reagents is just H3O plus. The steps for acid hydrolysis of esters are going to be a little bit different, because again, now we are dealing under acidic conditions. When we have acidic conditions, understand that the first step of the reaction is going to be the protonating of the oxygen in your C double bond O. And that's exactly what we see in the first step. Then after that, water is going to be our nucleophile and is going to add to the carbon in the carbonyl. We are going to be forming a tetrahedral intermediate. And in this molecule, remember, we're going to deprotonate the water that was the nucleophile. That's where we see that proton transfer. Now, once that occurs, remember that in this system, what I'm putting in the dotted line overall is going to be our leaving group. And because we're under acidic conditions, it cannot just be kicked out of the system. We have to protonate it so it leaves as an alcohol molecule. So that's where we see that second proton transfer. And the alkoxy group is converted into the leaving group. So after that, we're going to be losing the leaving group. But it, as I just mentioned, is in the form of an alcohol. Under acidic conditions, we cannot suggest that we're going to form an alkoxide. So the negative charges cannot be proposed. Now, when the lone pair of electrons from the oxygen comes down to reform that C double bond O, understand that then the alcohol leaves as a leaving group, and the last step of the reaction, we're going to deprotonate, specifically the carboxylic acid that was formed when the alcohol was formed. So overall, as you can see, this is the alcohol that we formed in the hydrolysis, and our carboxylic acid is the other product. So whenever we have hydrolysis of esters, again, we're going to have two products, and we already have the mechanisms for base hydrolysis and acid hydrolysis. Esters can also undergo aminolysis. So understand that in this case, what we have is the formation of an amide. So when we have an ester reacting with an amine, we are going to be forming an amide. As you can see illustrated in this reaction, we are taking an ester and reacting it with ammonia. And in turn, the group that is bonded to the single bond oxygen is going to turn into an alcohol. Now, understand that the overall equilibrium of this reaction favors the formation of an amide, okay? But amides, remember that they are going to be more stable, aka less reactive than esters, so that's why that is favorable. Now, the synthetic utility of this reaction specifically, because the process is very slow, is limited. So it's not the most elegant way to make an amide, okay? It is more efficient to make an amide from an acid chloride. So understand that typically when we're proposing the production of an amide, this is not going to be the most elegant reaction that we can have.